Logs don't enter a pencil factory as wood for writing. They enter as a dimensional stability problem. A pencil has to hold a brittle graphite core without cracking, stay straight through drying and painting, and sharpen predictably without splintering. So the plant starts by controlling moisture, grain direction, and density long before a single lead is made. Most high-volume pencil factories use incense cedar, basswood, or gelatong because these species machine cleanly and sharpen smoothly. Incoming timber is kiln-dried to a tight moisture range, so it won't warp later when lacquer cures under heat. Moisture probes and weight-based sampling verify every lot, because a few percentage points to wet can cause glue failure and paint blistering. While too dry increases chipping during milling, the wood is broken down into boards, then precision milled into thin slats, typically a few millimeters thick and wide enough to yield multiple pencils across. High-speed planers and multi-blade saws cut thousands of slats per hour, and laser thickness gauges check every piece in line. The reason factories measure thickness constantly is simple. The graphite core must sit at the center of the finished pencil, and any thickness drift shifts the core off-center, which creates weak walls on one side and breakage during sharpening. After slat sizing, the line turns into a CNC woodworking operation. Multi-spindle grooving machines cut parallel half-round channels into each slat, one groove per future pencil. Groove depth is micrometer controlled because it sets how much wood surrounds the core. Vacuum hold-down tables keep slats flat, and dust extraction runs continuously because Cedar. Dust is both a fire risk and a surface contamination risk that weakens adhesive bonds. While wood is being grooved, the factory is also manufacturing the lead, which is not lead at all, but a fired ceramic-like graphite rod. The performance of a pencil darkness, smoothness, and hardness is engineered at this stage by the ratio of graphite to clay and the firing temperature. More clay makes a harder, lighter line that holds a sharp point longer. More graphite makes a softer, darker line that wears faster but feels smoother. The raw materials arrive as fine powders, and the plant treats them like recipe-critical inputs. Graphite particle size affects smoothness and sheen. Clay mineral composition affects strength, and impurities can cause scratching or inconsistent color. Automated batching systems weigh graphite, clay and additives like binders into mixers. And the mixture is hydrated into a plastic dough. High shear mixing is used to break up agglomerates because even small lumps become weak points that cause the core to snap. Inside the wood, that dough is formed into continuous strands by extrusion. A screw extruder pushes the material through a die that sets the core diameter. And the extrusion rate is controlled tightly because diameter affects both writing feel and break resistance. The strands are cut into pencil-length rods and dried slowly to remove free water without cracking. Drying is staged because the cores shrank as moisture leaves. And too fast drying creates internal stress that shows up later as brittle leads. Next comes firing, the step that turns a soft extrudate into a strong, wear-resistant writing core. Cores travel through continuous kilns where temperature ramps are controlled in zones to prevent thermal shock. During firing, clay particles sinter and lock the structure while graphite remains stable, creating a composite that can resist pressure yet still abrade onto paper. The kill curve determines final hardness as much as the recipe does. So factories log time temperature profiles as a core quality fingerprint. After firing, many plants impregnate or wax the cores. Waxing fills micropores, reduces friction, and improves smoothness, which is why a good pencil feels buttery rather than scratchy. The cores pass through heated wax baths or vacuum impregnation chambers, then cool to a stable dimension before assembly. Inline optical inspection checks straightness, surface defects, and diameter, because a slightly bent or oversized core will miss a line in the groove and cause future breakage. Now the factory joins wood and core into a single engineered laminate. A grooved slat is coated with adhesive in a controlled film thickness, typically using roller coaters that deliver uniform coverage without squeeze out. The graphite rods are placed into the grooves at high speed by automatic layup machines that pick, align, and seat each rod. A second slat is laid on top like a lid. Creating a sandwich where each core is enclosed. Between two half channels, this sandwich is pressed under. Controlled pressure and time so the adhesive weights the wood fibers and locks the core in place without crushing it. Press parameters matter because excessive pressure can deform the core channel and stress the rods, while insufficient pressure creates voids that allow the core to rattle and fracture under writing loads. The pressed panels are then cured, sometimes at ambient conditions, often in heated tunnels to accelerate throughput for factories producing hundreds of millions of units per year. Once cured, The panel is essentially a multi-pencil blank. Multi-blade saws or profiling cutters slice the panel into individual pencil sticks. And this is where precision translates directly into yield. If the cut line wanders, one pencil becomes too thin and another too thick, and the entire batch fails. Sharpening and strength tests. Factories use servo-driven feed systems, carbide tooling, and real-time dimensional feedback to maintain straight cuts at high speed. Shaping comes next. And the geometry is selected for brand and ergonomics. Hex for anti-roll and grip. Round for simplicity. Triangular for training or comfort. Shaping machines use rotating cutters that profile the stick along its length, and they're tuned to avoid tear out at the grain. Tool wear is monitored because a dull cutter doesn't just look rough. It creates micro cracks that can propagate when the pencil is sharpened. Before painting, the wood surface is sealed. Raw wood absorbs finish unevenly, so pencil factories apply a base coat or sealer that fills pores and stabilizes color. Some operations use water-based sealers to reduce VOC emissions, while others use solvent systems with recovery and filtration. Either way, the coating line is designed for speed and cure control. Dip coating. Curtain coating or spray systems apply consistent thickness. Then the pencils pass through drying ovens or UV curing tunnels depending on the chemistry. The iconic yellow pencil isn't one thick layer. It's usually multiple thin coats. Thin coats reduce runs, improve gloss uniformity, and resist chipping. Between coats, pencils are tumbled or conveyed in fixtures that keep them separated so they don't stick. Drying ovens maintain controlled airflow and temperature, because too much heat can warp wood or weaken the glue line. While too little heat slows production and traps solvents that cause later tackiness. Branding and grade marking are applied with high-speed stamping. Foil stamping presses metallic or pigmented foil onto the lacquer, and the pressure and dwell time are tuned so the stamp bonds without crushing the wood. Inkjet printing is also common for variable data like batch codes. And machine vision verifies legibility because a smudged grade mark creates downstream sorting problems and retail rejects. If the pencil has an eraser, ferrule assembly becomes a metal forming and crimping operation integrated into the line. Ferrules are typically aluminum, fed in bulk, and oriented by vibratory bowls. Erasers rubber or vinyl compounds are cut to length and inserted. A crimping head compresses the ferrule onto the pencil end, with a controlled deformation pattern that grips the wood without splitting it. The crimp must hold through repeated erasing forces. So factories test pull-off strength and monitor crimp geometry with cameras and go-no-go gauges. Eraser performance is its own material science problem. A good eraser needs enough abrasiveness to lift graphite without tearing paper, and it must resist smearing and hardening over time. That's why eraser compounds are tuned for plasticizer content and filler particle size. And why plants store them in controlled environments to prevent drying and shrinkage before assembly? Sharpening, when done at the factory, is the final mechanical test of how well everything upstream was controlled. High-speed sharpeners cut a consistent cone and expose a centered core. Off-center leads show up immediately as thin wood walls and frequent tip breakage. Shavings extraction is critical because wood and graphite dust are combustible. So sharpening stations have dedicated vacuum systems, spark detection, and dust collection designed to meet fire safety standards. Quality control is continuous, because a plant making 500 million pencils a year cannot rely on end-of-line inspection alone. Core strength is measured with bend tests and brake force fixtures. Writing performance is checked by automated scribers that apply consistent pressure and speed, measuring line, darkness, and uniformity. Adhesion is tested by sharpening and drop tests because internal core bonding determines whether a pencil survives shipping and classroom use. Even the feel of writing is quantified. Factories measure coefficient of friction indirectly through torque and force during automated writing tests. And they correlate those results back to wax impregnation, graphite particle size, and firing curves. When a line drifts, operators don't guess. They adjust a parameter with a known effect, like kill temperature zone balance or wax bath temperature, and verify with a closed-loop sampling plan. Efficiency at this scale depends on minimizing waste at each conversion step. Wood offcuts become fuel for boilers or feedstock for engineered wood products. Graphite dust is captured and sometimes recycled into lower-grade cores. Coating over spray is filtered and recovered where possible. Tooling is managed as a predictable cost with scheduled changeovers. Because running cutters past their optimal life creates scrap far faster than it saves on tooling. The high-tech part of a pencil factory isn't a single robot. It's the way the plant turns natural variability into statistical uniformity. Wood is scanned, dried, and machined to tight tolerances, so it behaves like an engineered substrate. Graphite and clay are processed like ceramics, fired like technical components, and treated to deliver a specific friction and wear profile. Assembly is executed with controlled adhesive films, calibrated pressure, and dimensional verification so the core sits centered in a stick that sharpens cleanly every time. A pencil looks simple because it's small, but it's the output of precision woodworking, ceramic processing, coating technology, and high-speed automation. When a factory reaches hundreds of millions per year, consistency becomes the product, and the pencil becomes a standardized mechanical system designed to convert hand pressure into a smooth, predictable line, billions of times, one stroke at a time.